Hello everyone, I hope you're doing well. Today I'm excited to share our project on designing and simulating a solar-powered absorption chiller system specifically for residential cooling needs. In this work, our aim is to use the TRNSYS software to simulate this project in TRNSYS. Throughout this presentation, we will explore how renewable energy can play a vital role in cooling, which is significant energy consumer in building. Okay, let's move on to the next slide. Okay, as you can see here, this is the configuration of our proposed system. The main idea here is to harness solar thermal energy to power an absorption chiller. By doing so, we can use from solar radiation as a key renewable energy source and a lower carbon emissions. Our system includes several key components: solar thermal collectors, a lithium bromide absorption chiller, thermal energy storage, and auxiliary boiler, and also several pumps here. Together, these elements work together in order to maintain indoor thermal comfort while maximizing energy efficiency. So, in order to accurately model our system, we utilize TRNSYS, which is an advanced simulation tool designed for transient energy systems. TRNSYS allowed us to replicate how each component behaves in real time and how they interact with one another. Moreover, we use a TRNSYS library in order to visualize better components in our simulation. We'll move on to the next slide. As it is mentioned here, let's talk about our components that are used in our simulation. First of all, weather data, an essential input for any solar-driven system. In our simulation, we use TMY2 format, which is a key component in TRNSYS. This data was crucial for reflecting the actual climatic condition in which our system would operate. Additionally, the plotter and printer, as you can see here. These components are essential for outputting simulation data, allowing us to monitor and analyze performance over time. Another key component is pump. As it is previously mentioned in other slides, there are several pumps in our circuit. It circulates the heat transfer fluid throughout the system in order to ensure a continuous flow of energy. We also included an auxiliary boiler which provides supplemental heating during times of low solar radiation, ensuring that the chiller operates reliably. Next, let's focus on the thermal core of our system. Solar collectors capture thermal energy from the sun, which is then stored in an insulated heat storage tank. This stored heat powers the absorption chiller through a cycle. We also have a thermostat that monitors indoor temperatures and triggers the system to maintain desired cooling levels. This combination of thermal collection, storage, and also intelligent control ensures consistent and efficient cooling. Finally, we incorporated a differential signal controller to enhance operational efficiency. This controller continuously compares temperature between the collector and the pump. Based on this temperature difference, it decides whether to activate components like collectors or not. This smart controller strategy helps us minimize unnecessary energy consumption and maximize the use of available solar heat. Another components here that we utilize them in our project is synthetic building. This type, which is a type in the TRNSYS library, that is a built-in component there. It specifies our cooling load during seasonal operation. In order to simulate our project more reliable and better, we can use dynamic load, which is type 682. But if we don't have any access to this library, I mean TRNSYS, we can use equation in order to have that components and that equations interchangeably. So there is no any worry here. Okay. Eventually, this is our configuration of our system, which includes several components that we discussed before. As you can see in the left-hand side of the page, there is a solar collector which absorbs solar radiation and transfers the heat to the heat storage. Then it will pump into the next circuit, which is an absorption chiller. In auxiliary boiler, when there isn't enough solar radiation, I mean when there is insufficient solar heat power, it will activate and supplement our cooling load. So, as we discussed before, we used synthetic building and also dynamic load for simulation better operational conditions in different seasons and also in different temperatures. So that's it for this part. Let's move on to the TRNSYS software. Okay, let's move on to the TRNSYS software environment. As you can see here, these are our circuits of solar absorption chiller system. In order to simulate, we need our weather data. So let's click on weather data. We can choose our city, which in this project we used San Francisco. In order to change your location, you can browse and choose your city wherever you want. Well, then we have to connect weather data to solar collector. Well, so we need some information here. First of all, we have to match dry bulb temperature to ambient temperature. Then we need to connect solar zenith angle to the same one. And exactly like solar zenith angle, we need to connect solar azimuth angle to the same comment. Next one is total tilted surface radiation for surface, which is connected to incident radiation, and also total diffuse radiation for surface, which can be matched with incident diffuse radiation. And also we need the angle of incidence for surface, which is matched with solar incidence angle. And eventually we use the slope of the surface, which can be connected to the collector slope. Okay. Then we need to match the pump to the solar collector. So by this link, what we need to do is to match and connect outlet fluid temperature of the pump to the inlet temperature of the solar collector. Then, as we discussed before, outlet flow rate is the same as the inlet flow rate, so we need to connect them. Well, furthermore, we need to connect solar collector to the heat storage. Now we connect outlet temperature of solar collector to hot side temperature. As we discussed before, by absorbing solar radiation, the temperature will increase, so we need to connect them. Moreover, the outlet flow rate of the solar collector is as the same as the hot side flow rate. So we connected them. In order to close our loop here, we need to connect heat storage to the pump by this blue line, and the temperature to heat source will attach to inlet fluid temperature, and the flow rate, as discussed before, is connected to inlet flow rate here. So let's move on to the other components, that is signal controller. It is necessary to connect solar collector to the signal controller. Here we need to compare the temperature, outlet temperature of solar collector, and link them to the upper input temperature of the signal controller. And also we need to connect the pump into the signal controller. Here we attach outlet fluid temperature of the fluid to the lower input temperature of the signal controller. Here, as it is mentioned, the output of the control function is connected to control signal. So here it will activate or unactivate the pump in the TRNSYS software. Okay, well, let's move on to the chiller side. This is the right hand side circuit. We need to connect heat storage to the pump by this red link. We connected temperature and flow rate to load to the same one, exactly, inlet fluid temperature and inlet fluid flow rate. Then we need to match pump outlet to the inlet of the auxiliary boiler. As it can be seen here, outlet fluid temperature and flow rate will be matched to the inlet fluid temperature and inlet fluid flow rate. Okay. Another component here is auxiliary boiler. We need to connect the outlet auxiliary boiler to the inlet of the chiller. So we need to match outlet fluid temperature to hot water inlet temperature and also the flow rate, like always. Then, as you see here, when the power of the heated water exhausted in chiller, it goes back to the cycle and continues through cycle. Okay. So by connecting absorption chiller to the heat storage, our circuit will be completed. And here our hot water outlet temperature will be matched with cold side temperature, and also the flow rate will be matched like always. Okay, so thermostat has one input and one output. Its input is outlet temperature of pump. Therefore, we connect them. So outlet fluid temperature will be connected to the monitoring temperature of thermostat. Then we click on the thermostat component. Here we need to set only first stage heating set point to 110 degrees, and other properties are set. And also the output of the thermostat is a control signal. When the outlet pump temperature is less than 110 degrees, thermostat will activate auxiliary heater in order to compensate this deficiency. Therefore, we connect the absorption chiller to the load by the upper line here. So we connect chilled water temperature to inlet temperature of the load and the flow rate as before. So by doing so, it provides our cold power here for our residential cooling or whatever we have, and then we connect absorption chiller to the load, which is, and the outlet temperature will be connected to chilled water inlet temperature. It will be roughly about 12 degrees. Yeah. And uh, finally, we connect load to the synthetic building. We discussed about this component before, which specifies our cooling load hour and cooling load seasonal operation during a year. As you can see here, we choose the start of cooling season, which is 2880 hour, and also we set peak cooling load hour of 14 hours. Yes, and other variables are set and we don't change them, they are constant. And as we mentioned before, our peak cooling load here is 140 kilowatts, which can be variable in your project, and you can change it whenever you want. And finally, we match the cooling load to the dynamic load of the circuit. Yeah. And well, before running our simulation, one step is left here. Let's click on the setting. As we discussed before, we need to analyze the cooling load in the hot water season. So we need to set the simulation start time, which is 2880 hour, till the simulation stop time by 6552. Yeah, so by setting this, now we can run the simulation. Everything seems fine. So this is the diagram of temperature in terms of time. As you can see here in the lower side of the page, this is the chilled water inlet and outlet temperature, which varies during the time. And also, this is the pink diagram, which states the cooling water temperature fluctuation during time. Now the simulation is completed. And yeah, as you can see, this is the fluctuation of water that enters auxiliary boiler, which is mentioned here by green color. The fluctuation is due to the solar radiation during the year. Yeah. And these are the above diagrams. Let's zoom in here. As you can see here, there are two diagrams. One of them is blue and another one is orange color. The orange one is the outlet boiler temperature, which enters the chiller. Yeah, and also the blue one. This is the outlet chiller temperature, or in other words, this is the generator outlet temperature. And as it is vividly mentioned here, there are some fluctuations during time, and it is normal. The reason is because of the fluctuation of the variation of cooling outlet temperature, and also the cooling load variation. Now let's move on to another diagram here. This is a diagram of a cooling load during the cooling season due to the synthetic load that we discussed before. As you can see, there are some fluctuations and variation over the year. Approximately in the middle of the cooling season, we need the maximum cooling load, which is about 400,000 kilojoule per hour. Yeah, and we need to change the y-axis tidal. It is not temperature, it is a cooling load. So let's move on to the plotter type 65C2, move on to the special cards, and now here we can change the tidal from temperature to cooling load. Yeah. So we change them. Now we can run the simulation again. Now we can see the results that are reformed. Well, this is the cooling load variation during the different hours of a year, especially in the cooling season. Hey guys, thanks for your attention. I hope this video was helpful for you, and this content can help you for your further TRNSYS project. Take care and goodbye.